Assalamu alaikum. This is our tutorial video on the Vienna 5G system level simulator for EEE 4854 course. My name is Ahmed Mshuk Rafid. My student ID is 2100212447. Our selected scenario is the ship scenario, the basic scenario. The control variable is the base station transmit power, and I will solely present it as I have no group partner. So there is six parts. First of all, why a system level simulator exists, the four-phase workflow, the code in the MATLAB, a real run, the result, and the limitations. So the Vienna 5G link level and Vienna 5G system level. So what's the difference? The link level, the link level simulator from the experiment tree generates coded waveform samples from one link, exact and expensive for a network with dozens of base stations, unaffordable. The Vienna the system level simulator, the Vienna 5G system level simulator uses the link abstraction. It computes the SNR from the network geometry, then looks the throughput up in block error rate curves, and those curves came from the link level simulator, which is why the link level gives you a curve and system level gives you a distribution. This is our flowchart for the execution. There are four phases. The phase one is the launcher cell simulate. So the phase one calls the launcher simulate, which builds the parameter objects holding every default, then lets the scenario file override what it needs. The phase two, the pre-generation. This surprises people. The whole network is built before any time passes. The phase three is the only place time advances. The outer loop over chunks and inner loop over slots. Inside one slot, the scheduler assigns resources block. Uh, the link quality model produces SNR, gives feedback, computes CQI and rank, and all the chunks are processed in the post-processing in phase 4. Okay. Here, chunks, segments, and time slots. Three timeline levels. A time slot is 1 millisecond. Small scale fading is constant inside it. Okay. Uh, and scheduling and SNR happens there. A segment A segment is a run of slots over which the target scale quantities stay fixed. A chunk is a block simulated independently over every time, separated by 50 idle slots, so the channel decorrelates. The consequence is the most amber block. More chunks by independent channel realization, which is what smooths a distribution. More slots per chunk by correlated sample at nearly the same cost. It is exactly why we raised the chunk count from 2 to 10. If you remember the sentence from this video, the SNR is computed, the throughput is looked up. The link quality model takes geometry, antenna gain, path loss, precoding, scheduling, and interference, and produces SNR computed. The link performance model compresses that with MIESM averaging, reads a block error rate curve, and returns transmitted bits looked up. Keep that in mind for the second half. When you see a SNR keep moving while throughput stands still, that is not a bug. This is boundary in a measurement. So there are five files decides everything you will see. The launcher, the simulate, the scenario file, and the two objects owning the chunk and slot slope. We added the scenario file and one driver script and never edited the shift file, so our baseline is reproducible by anyone. Let me show the real files rather than the code. So here you can see the real files here. This is the the folder, and you can see this is the directory I have selected, and these are the files. uh, so I have opened all the files which I will show, and so first the launcher example .m. uh, the shift launcher, this is the shift launcher. The line matters here is it calls the simulate, the simulate function, and passes at scenario.basicScenario. uh, so then you'll see the basic scenario. This uh, this is our selected scenario and the configuration file of the whole simulation: timeline, region of the interest, carrier, transmission mode, scheduler, walls around the region, one base station, one user. Okay, so you can see. So you can see the basic scenarios here, and this is all the parameters is given here. And so now if we go to the IoT scenario, uh, our parameters are copied here, and there are all the parameters also here. This is the thing. If I show you which one is the thing, yeah, this is the base stations parameter, what will be the parameters, and the all the things. This is the users parameters and the interfering base station, so all the parameters are there. So, and there is the user speed, I think that is the user speed is given here. Oh, you can change the parameter as well. Now, so this is our main function. So uh, here if I point out ptxw, this is the our main control variable in what. This is our driver as well. This is the transmit power, 8 value from 40 watts down to 4 microwatt, run twice, once as shift, once as an interferer. So we predicted two parameters by hand before running anything, because a prediction written down in advance is what let you catch your own mistakes later. So so our second prediction: experiment B adds an identical base station of at 170. This is the 170 miles away, 83.1 decibel of free space loss, and both transmitters scale together, so no ratio never changes. 83.1, so 83.1 minus 70, so around 13.1 decibel. A hard SNS ceiling is the geometry alone. So now if we go to the MATLAB and run our simulation, so this is our main simulation file. This is our main, a main file where we'll run. So if we press run, then if we expand it, so it runs chunks by chunks. Each simulated each simulating chunk line comes from the loop in the local simulator local simulation dot run. Then here you can see the plots. There will be multiple plots, and after the run, I can show you that. There will be 16 runs. So here you can see all the things are calculated, and there's the graph. If the graph is there, and everything is saved in the files in the location, I'll show you. So everything is saved in the IUT results. Okay. So if I show you, this is the IUT results. This is what these all the graphs are saved. So I ran previously, and I also saved the results in my slides, so I can present it to you in a good manner. So if I show you, so there are two plots. So experiment A. So on the left side, this is the experiment one, experiment A. On the left side, this is the straight line, no interference, no SNR. Denominator is thermal noise, and alone, and the SNR tracks the power decibel for decibel, the 68.4 at 44 at 46 dBm, following exactly 10.0 decibel per 10 dBm steps. Okay. Experiment B rises with it while noise dominates. Well, the noise dominates the flatten at 13.11. Okay. So on the right side, the throughput is 159.74 megabits per, whatever the unit is. The identical number at 36, 26, and 16 dBm. And the flat, while the SNR behind it falls 30 decibels, then it collapses. Okay. 157, 101, and 36, 18. So this is the points for the things. The required baseline versus modified comparison. The baseline is 46. So the baseline is 46 dBm, SNR 68.44. Okay. The maximum throughput is 159.74, and the modified is 101.33. Yeah, the CQI level for the baseline 46 dBm is 15, and the modified minus 4 dBm is 12.27. So that's the thing. So the observation is the SNR falls. The SNR fails decibel for decibel with transmit power, but throughput does not move at all over the 30 decibel of the sweep, uh, and the reported CQI sits pinned at 15. The interference, the plateau belongs to the LPM, not the CQM. Once the effective SNR sits above the operating point, the highest CQI, the SNR to transport block size mapping saturates at the extra received power is discarded. This is exactly the abstraction boundary from the slide 6 visible in the measurement. The engineering consequences, this is the real deployment capacity at the cell edge is set by geometry and the interference, not by turning the power up. The second consequence of of our experiments is the path loss on this link is 70 dB minimum capturing loss, not the 63.8 dB free space value. So the moving the user would have been a poor choice of control variable. This is the part we did not predict, and I want to straightforward about it. With the minimum interfere present, SNRS is healthy 13.11, and the mean user throughput is exactly 0. The mean BLER in the experiment B is 8.8 0.893 across the whole high power range. The EV reports CQI of 11.31 and rank 1.87. So there's a thing, but so two further cases we could not separate 1 millisecond feedback delay against the 926 Hz Doppler and a layer scaling uncertainty the simulated source flag itself. So the scaling established, the rank over selection established, which is the remaining two dominates not established. To close the interference argument, 70 decibel of the desired link, 83.1 interference link, and 13.111 decibel predicted and 13.1 predicted and measured 13.111. And this is why a system level simulator exists. Quantity uh, the quantity that decides the performance is a ratio between the two propagation paths, and no amount of link level detail on one of them can reveal it. So briefly, what this cannot tell you: one user saw no scheduling contention, shadow fading off, free space free space path loss, one interfere, no position, 100 slot samples. So at the link level, adaptation failure is diagnosed, not fully resolved. Three things we can say now: the extract transmit power stops buying throughput once the effective SNR reaches the top of the CQI table. The selling belongs to the link performance model. With one co-channel interference, extra power stop buying SNR at all. Selling belongs to the geometry. And thirdly, the result we did not predict. The interferer present in the feedback keeps asking for two layers: link adaptation over overreaches, and median throughput falls to zero at healthy 13 dB SNR. So this is the reference we have. It's a reference file I have given. So this was all about the projects. Thank you very much. Assalamu alaikum.